Welcome. This guided tour will cover how to approach formulating an object-oriented solution as a repeatable process. From specification to implementation, creating a reusable software component. This video is part 1 of 3. This presentation will walk you through a simple problem analysis to formulating an object-oriented design for developing a class. Up to this point, you have learned good structured programming techniques and developed a host of programming skills, such as making decisions, looping, using pre-written classes, and creating objects to solve programming problems. You have begun analyzing problem specifications in terms of nouns and verbs. The nouns help us to discover possible classes, objects, and the properties of the objects, while the verbs guide us in identifying the methods the class objects will need to provide. We will use this noun-verb analysis technique from now on to develop our object-oriented designs and programs. Our approach is iterative in nature. We will look to find the cooperating objects and consider the relationships between them. We will use the class as the foundation for describing self-governing objects, thinking about them in a broad sense so that they are reusable, coding them carefully so that they cannot be corrupted, and thinking deeply about them and testing them carefully to be sure they work 100% of the time under normal and abnormal conditions. This graphic is a picture of how we will be approaching solving our programs from design through to code. Now first we're going to need to analyze the requirements. These are provided for us. For instance, I will provide you with a specification and you will design, code, and test a solution. This is the way software is developed in industry. We are modeling that approach, but for a much smaller, simpler programming problem. We want to develop the habits and techniques that will work when the problems become larger and more complex, which of course they will as you move along in your education and into the real world. One other note before we consider this picture. At each phase, there is important documentation that is produced. This is critical for teams of programmers and software engineers to be able to work together to build software. A popular form of sharing and exchanging information about the software under development is accomplished by using the UML, the Unified Modeling Language. We will be practicing with just a few of the UML diagrams. More to come about that soon. Okay, let's look at this closely now. We see Analyze Requirements at the top, and moving clockwise, Design, Code, and Test. The solid blue lines represent the ideal. If we follow this in a clockwise fashion, from the analysis we want to see the big picture. What are the objects and how will they interact? The design will describe them in terms of their responsibilities as self-governing objects in the overall problem domain. Then we need to code those classes by coding their components, data and actions, which in Java terms means their variable members and method members. Here we need to be paranoid programmers. By using secure coding devices such as keeping the data members private and restricting access to methods on an as-needed basis. After constructing a class, we build a set of test cases for objects of that class and thoroughly test the objects using typical values, critical values, and invalid values. We don't want an application to be able to break any class objects that get created. There can and should be back and forth, stepping and working between the different phases, as we see here by the blue arrows. We tend to go back and forth between analysis and design and code, and coding and testing. If we have a well-planned design, this iterative process helps us build robust software that can be easily maintained in terms of adding new features, and finding and fixing bugs. Sometimes we get into a phase and notice significant issues, such as trying to code for something that was left out of the design. In that case, we need to backpedal from coding to analyzing the requirements again and reconsidering how that missing piece will fit into the overall design. This can occur when we are testing too. Perhaps we left some important piece out of the design and we catch that when testing. That's not so bad. But notice the red dashed arrow. This is certainly more problematic. We are in the testing phase and we notice a problem. Maybe it's a timing issue. The program design and code produce software that is unacceptably slow. Now we are taking a 3-step leap backwards, and this is likely to cause a lot of disruption to the overall software product as we have to reanalyze the design and code and then test again. We are going to create a reusable component, a counter, from start to finish. Here is its specification. A counter consists of a value and an upper limit. The counter should initialize its value to 0 and set the upper limit. The user should be able to increment the value of the counter as well as set the value between 0 and the upper limit. Object-oriented design starts from analyzing the specification, working from the description, and picking out the nouns. This will shed light on the likely data members, which will be coded as instance variables, also known as fields. As I read through the narrative, I will mark the unique nouns that we encounter. A counter consists of a value and an upper limit. The counter should initialize its value to 0 and set the upper limit. The user should be able to increment the value of the counter as well as set the value between 0 and the upper limit. So here are my list of unique nouns. Now that we have identified the possible data members or fields of this counter, we want to consider this description again in terms of the verbs. We want to identify the verbs in the narrative, and this will help us identify the actions, in Java speak, the methods that we will need to provide. A counter consists of a value and an upper limit. The counter should initialize its value to 0 and set the upper limit. The user should be able to increment the value of the counter as well as set the value between 0 and the upper limit. Since this is a simple one-object description, we don't need to consider yet how it interacts with other objects in a problem solution. Once we identify multiple objects in a design, then we will need to consider how these objects work together or cooperate to meet the problem requirements. The only other object in this description is the user, which could be considered an application. We will soon see that the UML diagrams can be a useful tool for succinctly describing these interactions as well as the class. Now we get to the fun part. We are going to code our first cut of this class. But we want to do that by hand. Here's our list of the nouns we found that will translate into the instance variables, value and upper limit, and the methods. We saw we needed to initialize our counter, set the value, and increment the value. So moving from the description here and our recorded nouns and verbs, we would translate the value into an integer member of the counter class. Upper limit will also be an integer. The initialize can be done using our constructor that accepts an input for the upper limit and we'll set the value to 0. We'll provide a setValue method that takes one integer input to set the value of the counter. We will also provide a getValue. Even though we didn't list that as a method from the narrative, we know that it's important to provide set and get methods for our variables. We'll provide a getUpperLimit method, but not a setUpperLimit. We will take that initial upper limit value and use that to construct the counter. There's our increment. And one other thing I notice is that we don't have any description here of how we are going to display the counter. So this is, again, that idea of going back and forth between starting to code, thinking about the design, thinking about those requirements. Although I did not see a show value, I'm pretty sure the application is going to want to be able to display the value of the counter. So we'll include a toString method to do so. The third part of considering our design for our class is the importance of limiting access of the class members. Here is where our approach really does diverge from CSC 121 structured programming. Remember, we are focusing on secure programming techniques. So we need to carefully consider which members of our class really need to be directly accessed from the application using our class objects. Think paranoid. We are restricting access as much as possible so that our class components never get corrupted. Rule number 1, we should always keep the class instance variable members private. The only exception to this is if you are providing a final variable which is inherently protected from being changed. That could be public. Rule number 2, provide setVariable and getVariable methods for the data members as appropriate. Notice that we don't need or want to provide a set limit for counter. Once the limit is set at construction time, it should not be changed. So this data member will only have a getUpperLimit method, not a setUpperLimit method. Number 3, make your objects self-governing. Let them manage their own affairs. We will only make methods public if they are truly needed by the application. For counter, the increment is definitely needed, so it will be a public method. toString as well. Our setters and getters are always made public, but it is not always the case that other methods should be public, and we will revisit this notion again later. Let's describe the class using a UML class diagram. We start by identifying the name of the class. Then we list the data members. Here we have value and upper limit. Now you need to carefully look at this diagram because there's a lot of information packed in here, and there is a style that we're supposed to adopt when we're doing the UML. This is because it's a consistent way that programmers and software developers exchange information. The minus signs in front of value and upper limit indicate they're private. After their names, we see the colons and their data type. The lower section describes the methods. We see the counter constructor that will have one input. That's for the limit. The increment method with a plus sign is also a public method. Its return type is void, and it has no inputs. Our setValue needs an integer input. It will be a void method. The getValue will return a copy of the value. That will be an int returning value method. We see getUpperLimit returns int, and the toString returns a string. Here is the way this will translate into Java code. Let's code this class in NetBeans. You can create a test counter project. The test counter will be the throwaway driver for testing the class. Create a new class for counter and build your class shell from the UML diagram. Here is my first cut. We see public class counter. Remember to capitalize the name of your class. That's standard practice. The counter consists of two integer members, value and limit, both made private. Again, this is standard practice. And we name the variables and the objects and the methods starting with lowercase letters. The constructor has to have the exact same name as the class, so it is named counter. Now our constructor accepts one input. This is for setting the upper limit. As a programming exercise, when you code your counter, you should make your limit a final variable. That way it can't be changed. We see the toString method, the increment, the set value that takes one integer input, the get value, and the get limit. Now we're ready to code. This concludes part 1 of From Spec to Code, Test and Implementation for a Counter Object. Happy coding!